Chapter 5, Describing Distributions Numerically, specifically discussing standard deviation. When a distribution is skewed, the median and IQR are the best way to describe center and spread since they are resistant measures. However, when a distribution is roughly symmetric, there are alternatives. To describe the center, we can use the sample mean, or average. To find it, simply add up all the observations and divide by the sample size. This is the regular average you've always seen. Add up all of the numbers and divide by the total number of numbers. In our book, they use the letter Y to represent observations in a data set. However, it is more common to use X bar for the sample mean, so that is what we will do. The sample mean is called X bar. Anywhere there's a bar over a variable, it is to indicate a mean. It is called the sample mean since it is computed from the observations in a sample. If we had conducted a census and had all the members of the population, we would use mu to denote the population mean, which would be the true mean. We use X bar to estimate mu since we almost always are using sample data. It is really hard to collect a census. A census would mean we need to get everybody in the population. So if we were trying to estimate something about people that live in Murray, i.e. their average water cost, it would be really hard to find out all of their information, but much easier just to take a sample of a few neighborhoods. Okay, and again, sample size is always denoted n. N equals the number of samples or people. So n equals 10, we sampled 10 homes. Here's another example. Maybe we were looking to find the average GPA of all Hillcrest High School students. I could get on Skyward and try to look all of that up, and it would be a huge pain. If I was able to, I would use mu to represent that average. Maybe it's 2.7. But much easier for me would be to take a sample of a few students, maybe just a few kids in some of my classes. So then I would use X bar. But I would need to be careful to make sure that the sample that I took was representative of the whole population, and we'll talk about that later. Graphically, the mean of a distribution is located at the balancing point of the distribution. The mean is the value that balances the deviations from the mean. So basically, it's just where it would balance. If this was a teeter-totter, it would balance here. In left-skewed data, the mean actually follows the outlier to kind of counteract this pulling or this long part of the shape. So it would be closer to the outlier, and same thing for right-skewed. Is the mean a resistant measure of spread? And the answer is absolutely no, or not. How is it affected by outliers and skewness? Well, they pull it towards that direction. For example, maybe the average class test score is 75%. And I use that to see how well you guys understand. If the average is 75, I would say, okay, that's pretty decent. Maybe I need to review a few things. But if somebody got the answer key and cheated, and got 102%, they even got the extra credit, now my average may look like 85. I assume you guys really know what's going on, and I move on. Obviously, the cheater's score influenced the average and raised it up towards the outlier. Another way to measure the spread of a distribution is to estimate the average deviations from the mean. This quantity is called the sample standard deviation, and we denote that by S of x. Standard deviation is another way to measure the variability of a distribution. And what we're going to do is to find out how far each value is from the mean. For example, in the dot plot below, the observations are 2 units from the mean on average. So they're saying that we have one value at 1, 2 values at 2, 1 value of 3, 1 value of 5, 2 values of 6, and 7. And they're saying the mean, notice that they're using mu, is 4 because this is all of the data points in the population we're talking about. Now we want to figure out how far away that data is from the average. Well, 1 is 1, 2, 3 spots away from 4, and it's less than it, so it's -3 away. Again, you could just say 1 minus 4 and get a -3. For 2 then, it's 2 less. 2 minus 4 is -2, and so on. I could fill in the table. Now we're trying to find something similar to the average deviations from the mean. Well, these are the deviations. Well, remember with average, we just would add them all up and then divide by the number of deviations. So let's go ahead and do that. -3 plus -2 plus -1, ... And unfortunately, the problem is when we do that, we get 0, and we'll always get 0. So to solve this problem, we will square each of the deviations before adding them up. And we'll explain why this works in class. So -3 squared is 9, -2 squared is 4. Notice we got rid of the negative sign, so they're no longer canceling each other out. Let me fill in that table. At this point now, we could add up all of these numbers. So the sum of x minus mu squared, add up all of these numbers and you'd get 36. And we want to divide it by the number of numbers, 1, 2, 3, 4, 5, 6, 7, 8. 36 divided by 8 then. Finally, we want to take the square root of this number. So the square root of 36 over 8 is 2.12, or the average number of deviations each data point is from the mean of 4. And we can call that the typical distance from the mean. Unfortunately, when we are trying to estimate the standard deviation from a sample, things get a little more complicated. First off, we do not know the value of mu and must use x bar as an estimate. Therefore, because the sum of the squared deviations from x bar will never be bigger than the sum of the squared deviations from mu, the quantity, the square root of the differences squared all over n, will underestimate the true standard deviation. This is true because x bar is calculated from the actual data and is the value that minimizes the sum of the squared deviations. There is no guarantee that mu will be exactly in the middle of the sample data. To compensate for this, we will reduce the denominator in the expression from n to n minus 1, giving us the following formula for sample standard deviation. So to help us understand why it's n minus 1, consider the case where n is 1 from a sample of size 1. We can estimate the average by the score divided by 1. But we have no way to estimate the variability from the mean since there is only one observation. Therefore, dividing the sum of the differences by anything other than n minus 1 would give us an estimate of 0 for the standard deviation. This would imply that the population had no variability. Although this could be the case if all the members of the population had the same value, it certainly wouldn't be true for more than a few cases. Dividing by n minus 1 makes the standard deviation undefined, which is clearly the more appropriate option when dealing with a sample size of 1, because we just have no idea. We can't estimate how far away the other numbers are when we only have one number to compare to. Estimating, the value we just found was standard deviation, but estimating the standard deviation from a sample instead of a full population is a little bit harder. First off, we don't know the value of mu, the actual average, so we must use x bar as an estimate, or the average of our sample. Therefore, because the sum of the squared deviations from x bar will never be bigger than the sum of the squared deviations from mu, because x bar has a smaller number of values in it than the full population, the value we find when we divide by n will underestimate the true standard deviation. This is true because x bar is calculated from the actual data and is the value that minimizes the sum of the squared distributions. There is no guarantee that the actual mean will be exactly in the middle of the sample data. So we're going to try that. We're going to generate 3 random numbers from 1 to 9 and calculate the sum of the squared deviations from the sample mean and from the population mean, where the mu is 5. What I mean by that, if you were to take the numbers 1 through 9, 1, 2, 3, ... up to 9, and find the average, so add them up and divide by all 9 numbers, you would get an average, or a mu, of 5. I am going to simulate taking a sample of the numbers 1 through 9. So assume that I had the numbers 1 through 9 in a hat. I reach my hand in and randomly grab 3, one after another. Again, if you did that, you couldn't get the same number twice, so if we get a duplicate here, we'll ignore it. We'll use our calculator to do that. We're saying random numbers 1 to 9. We're going to draw 3 of them. And we got the numbers 1, 8, and 6. Next times 2, 9, and 7. And that one doesn't count because we have a duplicate. 9, 1, and 2. Here I've written down the sample data. So we got 1 at 1, 8, and 6. 1, 2, 9, and 7, and 1, 9, 1, and 2. I found their averages. Notice that they vary when we know the true average is 5. And we're going to go ahead and use this data and find the differences of their data minus the sample average, which would be this. So 9 minus the sample average of 4 gives a difference of 5. And we did that with all of them, and then we squared it and added them up like we did with the formula, and we got a difference of 38. If you do it with the actual average of 5 from all numbers, you get a difference of 41. No matter what, the sum of the squared deviations from the sample average will never be bigger than the sum of the squared deviations from u, and we saw that here. Here we had 38 versus 41. So, to compensate for this, we reduce the denominator in the expression from n to n minus 1, giving us the following sample standard deviation formula. So why n minus 1 but not n minus 2 or something else? Basically, we can think of the simplest case. If we had a population of just 1, the only way to properly estimate the standard deviation would be to divide by n minus 1. Let me read it. From a sample size of 1, we can estimate the mean of our sample value divided by 1. But we have no way to estimate the variability from the mean since there is only one observation. We don't know how much it's varying. We have nothing to compare to. If we divide the numerator, so the value of 1 minus the average of 1, which is 0, by anything other than n minus 1, we would get an estimate of 0 for the standard deviation. This estimate would imply that the population is not varying at all, which could be true if all the numbers were 1. But we have nothing to suggest that. Instead, if we divide by n minus 1, so 1 minus 1, or if we divide by 0, it'll make the standard deviation undefined, which is clearly the more appropriate option when dealing with the sample size of 1. Also, dividing by n minus 1 makes the sample variance an unbiased estimate of the population variance, which means it's a pretty good guess of the actual population variance. Variance is just the standard deviation squared. And you will hear this over and over again. Sometimes we say standard deviation, sometimes we say variance. Lastly, what if the last value in the data set above was 18 instead of 7? Calculate and interpret the new standard deviation. Is the standard deviation a measure of spread? And I will let you do that and bring it to class. I skipped the calculator instructions that we went over in class, and I'm looking at the last example on these notes. For the following sample of IQ scores, calculate the mean and standard deviation. Then sketch a dot plot, and then on the axis label the mean plus or minus 1 standard deviation, 2 standard deviations, 3 standard deviations, etc. What we're going to do, or what we could do, is we could put this data in list 1 and do one variable stats just like we did in class, and we would find out that the mean IQ score is 107.1, and the sample standard deviation given by S of x is 16.4. I then have plotted all of this data on a dot plot. And then what I meant by this part right here, the mean plus or minus 1, 2, or 3 standard deviations, I took the average and added to it one standard deviation of 16.4. Do that again, and I get 139.9. And again. And then I could also subtract 107.1 minus 16.4, and I'd get 90.7, and again and again. Notice that once we get 3 standard deviations away from the mean, all of the data is in there. It's also asking you to find the percent of the data in each spot, but we'll talk about that later.